Look at a candle. I mean, really look at it. Not the way you learn to look at things in school, where you're just waiting for the teacher to hand you the answer. Actually look. Because right now, in front of you, something is happening that no physicist alive can fully explain. And I don't mean that the way motivational speakers mean it. I mean it the way the data means it. The way peer-reviewed experimental results mean it. Results that have been replicated, confirmed, and then quietly shelved because the implications are too uncomfortable for a textbook. That flame is producing light. You know that. You've known that since you were a child. But here's what nobody told you. There is no mechanism inside that flame that we can point to and say, with certainty, that is the thing doing the generating. And the moment you understand why, the moment that sentence stops sounding like philosophy and starts sounding like physics, your entire model of reality is going to need reconstruction. If you can't handle that, close this video now. Seriously. Because what I'm about to show you isn't a theory, it's a measurement problem. And measurement problems don't resolve themselves just because you want them to. Still here? Good. That already tells me something about you. Before we go any further, I want to be transparent with you about something. Because this channel doesn't do what most science channels do. We're not going to quote a famous physicist and let their authority do the work. We're not going to put Einstein's face on screen and hope the association makes you feel like you've learned something. That's not respect. That's theater. What we're going to do is walk through the data. The actual experimental measurements. The actual numbers that come out of actual labs. And then, and this is the part that makes this channel different, we're going to hand the interpretation back to you. Because the data doesn't tell you what to believe. The data tells you what happened. What it means is a question that physics, right now in 2025, cannot answer with consensus. And any channel that pretends otherwise is lying to you. You deserve better than that. So here's the deal. I'm going to show you something real. You're going to be confused at points, and that confusion is not a failure. It's the accurate response to genuinely unresolved science. If you feel frustrated, that's not because you're not smart enough. It's because this problem has frustrated people with Nobel Prizes. Stay with it. Now, let's build the foundation, because without it, everything I'm about to show you will feel like a magic trick instead of a physics lesson. And I'm making this deliberately demanding, not to be difficult, but because shortcuts here will cost you later. Every concept I'm about to give you is going to come back harder and sharper in the second half of this video. If you want the rewatch value, pay attention now. First concept, an electromagnetic wave. When most people hear electromagnetic wave, they think radio towers, they think microwaves, they think something generated by technology, by a device with a plug, with a power source, with wires doing something deliberate. That intuition is wrong, and it's wrong in a way that matters. An electromagnetic wave is, at its most stripped down, a disturbance in two coupled fields, the electric field and the magnetic field, that propagate through space by continuously regenerating each other. A changing electric field produces a magnetic field. That changing magnetic field produces an electric field. Back and forth, forever, without any external input once the wave is launched. Maxwell described this mathematically in the 1860s, and the equations were so clean, so perfectly self-consistent, that when he solved for the speed of propagation, he got a number that exactly matched the measured speed of light. Not approximately, exactly. That wasn't a coincidence. That was the universe telling him something. Light is an electromagnetic wave, and electromagnetic waves, once they exist, sustain themselves. They don't need a power source to keep traveling. They need a source to be created. That distinction is everything. Second concept, the quantum field. Here's where your school curriculum failed you. Because when quantum mechanics arrived in the early 20th century, it didn't just modify classical physics. It replaced the ontology, the basic picture of what exists. In quantum field theory, the most rigorously tested physical framework in human history, the fundamental entities are not particles, they are fields. Fields that exist everywhere, at every point in space, even in what we call a vacuum. The photon, the particle of light, is not a tiny ball traveling from the candle to your eye. It is an excitation of the electromagnetic quantum field, a ripple, a vibration in something that was already there. And this is where things get genuinely strange. The quantum field is never truly at rest. Even in a perfect vacuum, no matter, no radiation, temperature at absolute zero, the quantum fields still fluctuate. This is not a theoretical artifact. It is a measurable physical reality. It's called the Casimir effect, and it was experimentally confirmed in 1997 with precision measurements that matched the quantum field theory predictions to within 1%. The vacuum isn't empty. It's seething with what physicists call zero-point energy. Fluctuations that are always there, always real, always doing something that classical physics has no language to describe. Third concept, thermal emission. The candle flame burns at roughly 1800 Kelvin at its hottest point. At that temperature, the carbon atoms and combustion byproducts inside the flame are in a state of violent chaotic motion. Electrons in those atoms are being excited, pushed into higher energy states by the thermal collisions, and then they fall back down. And when they fall back down, the energy they release doesn't disappear. Energy can't disappear. It gets emitted as a photon, a quantized packet of electromagnetic field excitation. This process is called blackbody radiation, and it was this exact process that broke classical physics in 1900. Because when physicists tried to calculate the spectrum of light that a hot object should emit using classical electromagnetic theory, they got a prediction that was catastrophically wrong. The prediction said that a hot object should emit infinite energy at short wavelengths. Not a lot of energy, infinite energy. This failure was so severe, so obviously absurd, that physicists named it the ultraviolet catastrophe. Max Planck fixed it, but the fix required something that disturbed him so deeply he spent years trying to find a way around it. He had to assume that energy is not continuous, that it comes in discrete, indivisible chunks, quanta. He didn't believe it was physically real at first. He thought it was a mathematical trick. Einstein later showed it wasn't a trick, it was the structure of reality. Fourth concept, the measurement problem. Now we arrive at the concept that ties everything else together and the one that has never been resolved. When a quantum system, like an electron or a photon, is not being measured, it exists in a superposition of states. Not, we don't know which state it's in, superposition. It is, in a mathematically precise and experimentally confirmed sense, in multiple states simultaneously. The wave function, the mathematical object that describes the quantum system, evolves smoothly, deterministically, according to the Schrödinger equation. No randomness, no collapse, just smooth, continuous, entirely predictable evolution. And then measurement happens, and the smooth evolution stops. The superposition results into a single, definite outcome. And here is the problem, stated as plainly as I can state it. The equations of quantum mechanics do not describe this transition. There is no term in the Schrödinger equation for measurement happens now. The moment of resolution, the moment the quantum becomes classical, is outside the formalism. The most successful physical theory in history has a hole in it, and the hole is exactly the size of the act of observation. Now connect that back to your candle. When the electron in that carbon atom falls from a higher energy state to a lower one, it emits a photon. Before that emission, the electron's energy state is described by a wave function, a probability distribution over all possible energy levels it could occupy. The emission event is quantum. The photon that results is quantum. It travels as an excitation in the quantum electromagnetic field, as a wave of probability amplitude until something interacts with it, until something measures it. And here is where your prediction comes in. I want you to actively participate in this, not just passively receive it. Before I tell you what the experiments show, I want you to commit to a prediction. Here is the setup. A candle emits photons. We place a detector at a distance. The detector can be switched between two modes. In mode A, it records which path the photon took. In mode B, it records only whether the photon arrived, with no path information. The question is this: will the pattern of photons arriving at the detector be different depending on which mode the detector is in, even though the candle is identical in both cases, and the photon has already been emitted before the detector mode is selected? Think about that. The photon left the candle. It's already traveling. And then we choose what kind of information we want to extract from it. Does that choice, made after the emission, affect the pattern? Commit to your answer, yes or no. The choice changes the pattern or it doesn't. The experiment I just described is a variant of the delayed choice experiment, first proposed by John Wheeler and experimentally realized in progressively more refined versions since 1984. The most recent high-precision versions, including a 2022 experiment published in Physical Review Letters using entangled photon pairs, confirmed the result that the data has been pointing to for 40 years. Your choice of what to measure, made after the photon is emitted, determines what the photon was doing during its journey. Let that land. I'm not going to smooth it over for you. The data says the photon's behavior during its transit is determined retroactively by what you choose to measure at the end of the transit. The measurement isn't passively recording a pre-existing reality. The measurement is participating in the construction of the result. Now, Who is generating the light from the candle? The thermal emission is real, the quantum field excitation is real, the photon is real. But when you ask for the precise state of the photon at any point before detection, the honest answer, the answer the data gives you, is that the question is not well formed. There is no definite state to retrieve. There is a wave function, a probability distribution, a superposition of possibilities that resolves only upon interaction. The flame generates the excitation, the field carries it, and what resolves into the light you experience, the specific photon, the specific wavelength, the specific moment of arrival, is a function of the measurement process itself. So now we have the data in front of us. And this is where I have to be methodologically honest with you again. Because what the data means, the interpretation of why measurement does what it does, is not agreed upon. There are three major frameworks that physicists and philosophers of physics use to make sense of this. And I'm going to give you all three. Not because one is right and I'm hiding it, because the data, as of right now, does not select between them. First framework, the Copenhagen interpretation. This is the oldest and still the most widely taught. In Copenhagen, the wave function is not a description of physical reality. It's a tool, a calculation device for predicting the probabilities of measurement outcomes. When you ask, what is the photon doing before measurement, Copenhagen says that question has no answer. Not because we lack information, but because there is no fact of the matter to be had. Reality, in this view, is not a thing that exists independently of observation. It is something that comes into being through the act of measurement. The famous phrase associated with Niels Bohr, "There is no quantum world," captures this. There are quantum phenomena, there are measurement outcomes, there is no underlying classical reality between them. Pro, it is mathematically clean, predictively perfect, and refuses to make claims beyond what the data supports. Con, it offers no account of what measurement physically is, why it causes collapse, or what observation requires as an observer. It punts the hardest question. Second framework, many worlds or the Everett interpretation. Hugh Everett in 1957 proposed the most radical solution to the measurement problem. Don't collapse the wave function. Don't introduce collapse at all. Let the Schrödinger equation run, always, everywhere, without exception. What happens when measurement occurs is not that one outcome is selected. It's that the universe branches. Every outcome occurs in a different branch of a universal wave function, and the observer in each branch experiences only their local outcome. In this picture, the photon from your candle doesn't collapse into one definite state. The universe, including you, branches into all possible outcomes. In one branch, the photon arrives at 342.17.001. In another branch, it arrives at 342.17.002. You only ever experience one branch, so it feels like a single, definite outcome. But all branches are real. Pro, no collapse postulate needed. The Schrödinger equation is universal and exact. Con, the branches have never been detected. The concept of probability becomes deeply problematic. If all outcomes occur, what does it mean to say one is more probable than another? And the ontological cost, an infinite proliferation of parallel universes, strikes many physicists as a price too high to pay for mathematical elegance. Third framework, hidden variable theories, specifically de Broglie-Bohm pilot wave theory. What if the quantum weirdness isn't a feature of reality, it's a feature of our ignorance? What if there are definite particle positions and definite trajectories, always, but guided by a pilot wave that we can only access statistically? David Bohm formalized this in 1952. In pilot wave theory, the photon from your candle has a definite position at every moment in time. It follows a definite path. The apparent randomness of quantum outcomes is not fundamental, it's epistemic. It reflects our inability to know the precise initial conditions. Pro, restores determinism, restores the idea that there is a real world between measurements. Con, pilot wave theory is explicitly non-local. The pilot wave for any particle is defined over all of space, and it is instantaneously affected by changes anywhere in the universe. This doesn't violate relativity in a way we can use to send signals, but it is deeply in tension with the spirit of locality that underpins modern physics. And it has not, despite decades of work, been successfully extended to a full relativistic quantum field theory. Three frameworks, no consensus, all supported by the data. Not because physicists are indecisive, but because the data genuinely does not discriminate between them at the level of measurement outcomes. The experiments that would select between interpretations either haven't been performed yet or may not be physically possible. You probably disagree with me that this question is open. You probably feel, somewhere in your gut, that one of these must be right. I'd push back and ask, on what evidence? The gut is not a measurement device. The data is. Now I want to tell you where I personally land on this, and I want to be very clear that what I'm about to say is philosophical position, not physics. I am not reporting a scientific conclusion. I am sharing an interpretive stance, and I'm doing that because I think intellectual honesty requires showing you that even the people who teach this material have to live with uncertainty. My stance. I find Copenhagen's instrumentalism increasingly unsatisfying in the light of 2024 and 2025 research. A paper published in Nature Physics in late 2024, building on the Frauchiger-Renner thought experiment, implemented what is now called the extended Wigner's friend scenario in a photonic laboratory setting. The results placed new experimental constraints on any interpretation that tries to maintain both the objectivity of measurement outcomes and the universality of the quantum state. What that means, in plain language, is that the two things you most want to be true simultaneously, that measurements have definite outcomes and that quantum mechanics applies to everything, appear to be in conflict. That result doesn't prove many worlds. It doesn't prove pilot waves. What it does is make the measurement problem harder to ignore, harder to dissolve with instrumentalist language, harder to treat as a mere philosophical preference with no physical stakes. The hole in the formalism is getting larger, not smaller, as experiments get more precise. What's your interpretation? I mean that as a genuine question, not a rhetorical device. Because the philosophical agency here belongs to you. You've seen the data, you've seen the frameworks, and the decision about what the data means is not mine to make for you. Tell me in the comments, not what you believe, what the data, as you understand it, points toward. There's a difference. And if you think I've missed something, if you think there's a framework I should have included, or a flaw in how I've presented the empirical constraints, that is exactly the kind of disagreement I want. That's not criticism, that's intellectual work. And this channel is built for people willing to do intellectual work. Now, before the next video, you need to understand something. Everything we've covered today, the quantum field, the thermal emission, the measurement problem, the three interpretations, all of it assumes that you understand what a quantum state actually is. Not the wave function as a formula, not the Schrödinger equation as a tool, the quantum state as a physical object, or possibly not a physical object, and what that distinction means for whether reality exists when you're not looking at it. Because the next video in this series goes somewhere that will make today look like the warm-up. We're going into the EPR paradox and Bell's theorem. And if you don't have a clear model of what a quantum state is, independent of measurement, independent of interpretation, Bell's theorem will feel like a magic trick instead of the most important result in 20th century physics. The next video is called Bell's theorem doesn't just break local realism, it breaks your definition of real. And it is not optional if you want to understand where this series is going. It is the load-bearing structure on which every subsequent argument rests. Without it, the later videos will make sense on the surface and fall apart when you push them. With it, the entire picture of what quantum mechanics is saying about the nature of reality will click into place, not comfortably, but precisely. That video goes live next. Don't let the algorithm decide when you see it. Here's something your brain is going to do in the next 48 hours. Forget 70% of this. Not because you're not intelligent, because that's what human memory does with dense conceptual material that doesn't have an emotional anchor or a physical practice attached to it. 70% in 48 hours. That's not a figure I invented. It comes from Ebbinghaus's forgetting curve, and it has been replicated consistently across a century of memory research. The only countermeasure that actually works is saving the video and returning to it. Not re-watching it entirely, just the sections that felt slippery. The quantum field explanation, the delayed choice result, the three interpretations. Those are the nodes where the architecture is load-bearing. If those go soft, everything built on top of them goes soft too. Save this video right now, not later, now. Because later is where 70% of good intentions go to die. If you're watching this as a standalone video, you need to understand that it is one piece of a deliberately architected sequence. This channel doesn't publish isolated episodes. Every video is a prerequisite for the next one. The concepts compound, the implications build. The picture that's forming about what quantum mechanics actually says about the nature of observation, reality, and the relationship between them cannot be assembled from a single video, no matter how thorough. Subscribe not because this video was interesting. Interesting is cheap, and there are 1,000 channels that do interesting. Subscribe because this series is building towards something specific, and missing even one video in the sequence means you'll arrive at the conclusion without the scaffolding that makes it hold. The subscribe button is an architectural decision, not a social one. And the next video, Bell's theorem, local realism, what it means for the word real. Don't think about it. Don't add it to a list you'll get to someday. Hit play now. The momentum you have at the end of this video is the highest it will be. The architecture of learning is built on that momentum. Use it. The candle is still burning. The flame is still doing that thing no physicist can fully account for, generating light through a process that is simultaneously thermal, quantum, and irreducibly strange at the level of what the measurement is and who or what is doing the measuring. The electron falls, the field excites, the photon propagates, and somewhere in the act of it arriving at your eye, in the act of your retinal cells responding to it, in the cascade of electrochemical signals that your brain converts into the experience of brightness and warmth, something that the equations don't fully capture is happening. Maybe that doesn't bother you. Maybe you're content to say the physics is the physics and the questions about what it means can wait for the philosophers. That's a defensible position. But I'd ask you, when has wait for the philosophers ever been where the interesting science happened? The interesting science happened exactly where people refused to be satisfied with the calculation and demanded to know what the calculation was about. A candle has no battery, no plug, no wires, no deliberate power source directing the emission. And yet it floods the room with photons that carry energy across space by disturbing a quantum field that was never at rest to begin with, a field whose behavior at the moment of its measurement remains one of the deepest open questions in physics. Who is generating the light? The flame is, the field is, the measurement is. And in some interpretation-dependent sense that none of us should pretend to fully understand, you are. Bell's theorem. Next video. Don't think, just hit play.